Hello, my dear students, and welcome in the Indoor Environmental Control course. I am Associate Professor Kareem Galal. We will start with the Indoor Environmental Control course. But first, what is the contents of this course? According to our curriculum, it is Principles of Lighting, Daylight and Artificial, in Buildings, Reducing Noise, and Enhancing Sound for Communication. Regulating heat transfer for occupant thermal comfort. Description of passive means for environmental control. Including presentation of scientific explanation and design guidelines for utilizing these means. Design guidelines for use in the preliminary schematic design phase. Now let us start with the first topic in our Indoor Environmental Control course. Lighting. The title of this lecture is Physics of Light. Okay, let's start. First, what does the expression of light mean? Light is a narrow wavelength band of electromagnetic radiation, from about 380 to 780 nanometers, is perceived by our eyes as light. The color of light is determined by its spectrum or spectral composition. A continuous spectrum of white light can be split by a prism into its components, which are perceived as colors. In the full electromagnetic spectrum and its solar segment, we can notice that the light wavelength band is very limited. Above this band, we can notice the telecommunication radiations, and below it the investigation radiations. But how can we define a certain color accurately? There are many surface color classifications to identify the accurate color definition. These are called color systems. The most comprehensive classification of surface colors is the Munsell system. This distinguishes three attributes: hue, value, and chroma. Hue is the concept of color, using the common terms, red, yellow, blue, etc., with transitional colors, e.g. green/yellow, and further numbered subdivisions. Physically we can identify it as the identifiable wavelength of light. Gives a color its name. Value, V, or lightness is the subjective measure of reflectance, light or dark appearance, measured on a scale of 0, absolute black, to 10, the perfect white. In conclusion, the value of a color is the tints or shades. It is how bright a color is. Chroma or saturation is the fullness or intensity of color. All colors have at least 10 classes, e.g. blue-green, but some colors can be very strong, having a chroma up to 18. It is the intensity or purity of a color how unmixed with white is. But these color models could not identify the all-color range that our human eye can recognize. These color models are matched with pigments and industrial purposes, but they are not matched with the lighting color range. The three-color theory of light distinguishes red, green, and blue as the primary colors, and any color can be defined in terms of its redness, greenness, and blueness. A 3D coordinate system can be set up to represent the three components, with the three axes being red, green, and blue. This diagram is referred to as the Cie Chromaticity Chart. The Cie color model covers all the available colors can the eye see. The software, display, imaging capture equipments, and printers have different ranges of colors to be recognized with these tools. This color range is called gamut. The differentiation between the color gamut from the software, display, and printing tools is the main cause of the not identical output colors. But wait, what are the complicated model forms for light space transmission of light? To understand these models, let's start with the main light definitions. The simplest luminous system consists of a light source, a lamp, a surface illuminated and an eye perceiving the light, both from the source and reflected by the surface. I, the luminous intensity of a source, measured in units of candela, CD, which is the international standard candle, is defined as the intensity of a black body of 1/60th square centimeters, when heated to the melting point temperature of platinum. It is the basic unit, from which all other units are derived. Phi, the luminous flux, or flow of light, is measured by the unit lumen, Lm, which is defined as the flux emitted within 1 steradian, SR, by a point source of I equals 1 CD, emitting light uniformly in all directions. Therefore, 1 CD emits a total of 4 pi lumens. The steradian. As the unit of 2D angle is the radian, where the length of the arc is the same as the radius, a full circle is 2 pi radians. The steradian, stereoradian, SR is the unit of 3D solid angle, that is subtended by an r⁴ area of the surface of a sphere of radius r. As the surface area of a sphere is 4 pi r⁴, the center of a sphere contains 4 pi steradians. E, or illuminance, the symbol E comes from the French éclairage, is a measure of the illumination of a surface. Note that illumination is the process, illuminance is the product. The unit is lux, Lx, which is the illuminance caused by 1 lumen incident of 1 meter square area, for example the incident flux density of 1 lumen per meter square. L, or luminance, is a measure of brightness of a surface, when looked at from a given direction. Its unit is CD per meter square, which is unit intensity of a source of unit area, source intensity divided by its apparent area viewed from the nominated direction. This table gives some typical values of flux output of light sources, illuminances, and the luminance of some sources and surfaces. Now let's start to explain the physics of light transmission through space. The inverse square law states that illuminance reduces in proportion to the square of the distance from the source. Interpretation of the inverse square law. The flux, which at a given distance, goes through a unit area, at double that distance, will go through 4 times that area. So the flux density, equals illuminance, reduces to 1/4. For example, to explain the inverse square law. If the luminous intensity, I, of the light source is 900 candela, CD, and the distance between the light source and the work plane is 3 meters. Assume the incident angle is perpendicular to the work plane, then illuminance, I, will be equaled 900/9 equals 100 lux. If the incident angle is 45, then the E will be 100 by cosine 45 equals 70.7 lux. Light incident on the surface can be distributed 3 ways: reflected, absorbed, or transmitted. The corresponding properties are reflectance, ρ, absorptance, alpha, and transmittance, tau, and in all cases ρ plus alpha plus tau equals 1. Surfaces may be classified, in terms of their reflective properties, as specular like a mirror, or diffuse such as the ordinary building surfaces, or transitional, which is giving a spread reflection, basically diffuse, but with some specular component, or semi-diffuse, all diffuse, but with some directional bias. Thanks for following me and hope that I have explained the topic well. This material is copyrighted. Associate Professor Kareem Galal 2021. All rights reserved.